Right. So let me just recall briefly that the previous time we have discussed dual spaces, and in particular we have defined transposition of a linear transformation, which, remember, is a linear transformation which goes in the opposite direction on the dual spaces. And we have proved some of its properties, and we also discussed double duals, right? And so we use double duals in particular to show that the double dual space is isomorphic to the original space itself. We have a canonical isomorphism, and used it to get to demonstrate that, in fact, every basis of the dual space is the dual basis of some basis of the original space, right? So we have developed some of these basic properties of the dual spaces. So before we continue with newer material, today I need to recall some more material from 115A. Yeah, so today we'll first of all recall eigenvectors and eigenspaces, which we will see soon is a special case of more general kind of subspaces, the so-called invariant subspaces and cyclic spaces. Yeah, but eigenspaces are the most important basic kind of those. So let me just write that this is a reminder from 115A. Okay. All right. So let's begin with the definition of a diagonal matrix. Yeah. So of course we all know what this is, but just to make sure we're on the same page. So a matrix A with n rows and n columns over some field F is said to be diagonal, yeah, or a diagonal matrix, if we have that the entry of the matrix in the position ij is equal to 0 for all I not equal to j. Okay, so it's diagonal if all the entries are 0 outside of the diagonal. Yeah, okay. And similarly, we define that a linear operator T on a vector space V. So remember, this is just a linear transformation from V to V, from V to itself. So a linear operator on T on vector space V, where we assume that the dimension of the vector space is finite, is said to be diagonalizable. Yeah, diagonalizable if there exists some ordered basis beta, let's say, for V, such that if we look at the matrix representing T with respect to this ordered basis beta, then this is a diagonal matrix. Diagonal matrix. Okay, so that's why we say diagonalizable. So it means it's possible to choose some basis with respect to which the matrix representing T is a diagonal. Yeah? But it might be true for one basis, maybe, but not for the other. So we are just saying that there exists a basis with this property. Okay, and let me recall some further definitions. So we need a certain notion of equivalence on matrices. So given AB, two n by n matrices over some field F. Yeah. So we say that these two matrices, A and B, are similar. Okay. They're similar if there exists an invertible matrix Q with the same dimension, so n by n over F, yeah, such that the matrix B can be obtained from the matrix A by multiplying by Q inverse. Yeah, so it's called conjugation. So if we conjugating by Q, we can obtain A from B. Conjugating by some invertible matrix. Okay, so this is one. And two, a matrix A, n by n matrix over F, is diagonalizable if A is similar to a diagonal matrix. Okay, so you see we have these two definitions of what it means to be diagonalizable. One is for linear transformations, one is for matrices, okay? And for linear transformation, you see it's a definition defined in terms of existence of some basis with respect to which the matrix representing it is diagonal. For matrices, we define it in a more computational manner. So we say that the matrix is diagonalizable if by conjugating by some invertible matrix, we can get a diagonal matrix. Okay, so for matrices, it seems like a notion which is more suitable for calculating with it, like for determinant numerically, for example. Okay, but as usual, we will see soon that there's a nice correspondence between diagonalizability for linear transformations and for their matrices, right? So remember, we always have this this correspondence between properties of matrices and linear transformations. Okay, so first of all, we have the following theorem. Okay, from 115a. So assume that T is a linear operator on V, a vector space of finite dimension. Okay, and assume that beta gamma are two ordered bases for V. Okay, so they can be distinct, they can be the same, doesn't matter. Okay, so then we have that the determinant of the matrix representing T with respect to beta is equal to the determinant of the matrix representing T with respect to gamma. Okay, so this is true. So what does it mean? So this means that the determinant of the matrix representing T with respect to some ordered basis beta, in fact, does not depend on beta. Okay, and hence it is called simply the determinant of T, of the linear transformation T. Okay, or notationally we write as a det T, determinant of T. Okay, so let me stress here that, of course, as we know, the matrix itself representing T might depend on the choice of the ordered basis. Yeah, so like these two matrices might actually be different. What the theorem says is that they have the same determinant. Yeah, so determinant does not depend on the basis, but the matrix representing T might depend on the basis. So it's important to distinguish these two. But since the determinant doesn't depend on the choice of the basis, we can just talk about it as the determinant of T, right? We don't have to mention beta. Okay, so we have this notion of a determinant of T, and let's recall some of the properties of this determinant. So, we have proposition, which summarizes some of the properties of this determinant covered in 115a. So the first property that T is bijective if and only if the determinant of T is not equal to 0. Okay, so we have that calculating this determinant allows us to understand if the linear transformation is bijective or equivalently invertible. Yeah, so the determinant is not 0. That's the criterion, and it's if and only if. The second remark is that if T is bijective, then we have that the determinant of the inverse of T, and it makes sense to talk about the inverse of T, right? Because when T is bijective, it has an inverse, of course. So the determinant of the inverse of T is given by the determinant of T to the power -1, okay? So it's just 1 over the determinant of T, yeah? So taking the inverse of linear transformation, inverts the determinant as well, okay? And the third excuse me, the third property is that if we have U, another linear operator on V, then the determinant of the composition, yeah, so T composition with U, which is again a linear operator on V, right? Because they're both linear operators on V, so their composition is also a linear operator on V. So the determinant of the composition is just the product of the determinants. So the determinant of T times the determinant of U. Okay. So you see the determinant somehow respects multiplication, commutes with multiplication, another way to say it. Okay. So we have some of these basic properties of determinants. Now we can connect diagonalizability for linear transformations and for their matrices. So this is the next theorem from 115a. We have that if T is a linear operator on V, where V is a finite dimensional vector space, and beta is an ordered basis for V, okay, so all the usual stuff, then we have that the linear transformation T is diagonalizable. Remember, in the sense of our earlier definition, if and only if we have that the matrix representing T with respect to beta is diagonalizable. Okay, so we have this this equivalence for diagonalizability between linear transformations and their matrices, as usual, right? So in the spirit of this correspondence, we always have correspondence between properties of linear transformations and matrices. Okay, so matrix representation gives us a way to produce a matrix starting with a linear transformation, right? We also, of course, have an inverse construction. How, if you are given a matrix, we can define a linear transformation corresponding to it, right? So let me recall this. So this is so-called LA construction. Yeah. So let me remind this. It's a standard way to produce linear transformation starting with the matrix. Okay. So given a matrix, this, let's say M by N matrix over some field F. Okay. We associate to it a linear transformation which we denote as L subscript A or LA, right? Like LA represent, I don't know. So from Fn to Fm, yeah, which is defined by taking the value of LA of X, where X is an arbitrary vector in V, yeah. So we take it to be simply A times X. So we multiply, yeah. So for every, and here we use column vector X in Fn. Okay. So we just so we can just multiply by A, and this gives us a linear transformation LA. Okay, and sometimes this LA is called the left multiplication transformation. But yeah, okay, it's just to remind you. So we have this method of getting linear transformation, excuse me, starting with a matrix. Okay. All right. So now let's go back to our discussion. So since we have this theorem, which tells us that a linear transformation T is diagonalizable, if and only if the matrix representing it is diagonalizable, we have the following corollary of this theorem. Okay, corollary. So we have that a matrix A n by n matrix over F, a square matrix over F, is diagonalizable if and only if the corresponding linear transformation LA is diagonalizable. Okay. So this is simply because the linear transformation LA is represented by the matrix A with respect to the standard basis in Fn, right? So then theorem applies and it gives us this corollary. Okay. All right. So now we define or recall, okay, I mean, you've seen it before, but let me recall the definition of some very important vectors and scalars and spaces associated to a linear operator. So definition one, so assume we have T, as usual, a linear operator on a vector space V, okay? And assume that the dimension of V is finite, okay? So then, actually, this is just the assumptions. So then we define one. So a non-zero, importantly, non-zero vector V in the space capital V is called an eigenvector of the linear operator T. Okay. If we have that T of V acts by simply multiplying by lambda, so lambda times V, for some lambda, a scalar in F, okay? So yeah, so an eigenvector for T is a vector such that if you apply T to it, all it does is scales it. Yeah, just makes it longer, or well, shorter, depending. So just scales it by lambda, some scalar. And in this case, when we have an eigenvector like this, excuse me, let me have a look for a second. There's a question in chat. So what is this corollary saying that isn't in the definition of a diagonalizable transformation? So it's very close, but strictly speaking, yeah. So strictly speaking, what it says is that the matrix is A is diagonalizable in the sense of diagonalizability of matrices, right? Remember the way we defined it earlier today. So for a matrix, it is diagonalizable if it is similar to a diagonal matrix. If and only if the corresponding linear transformation is diagonalizable. And for linear transformation to be diagonalizable means that there exists some basis. So here we're using this definition, right? So there exists some basis such that its presentation with respect to that basis is diagonal. Okay. So these are two different statements, but they're equivalent. So what it says, you don't have to look to search for all possible bases in the world to check it, for example, but it's enough to check it for the matrix A itself that it is diagonalizable. Yeah, do you agree? I mean, they're equivalent a posteriori using the theorem, but I don't think it's obvious because these are two different definitions in principle, but they're connected because of this corollary. They're the same essentially. Okay, all right. So let's go back to our definition. So we have eigenvector. So we define an eigenvector, right? But now this lambda. So then this lambda, a scalar, yeah, is called an eigenvalue Okay, so it's an eigenvalue corresponding to the eigenvector V. Okay, so just from the definition, every eigenvector has a corresponding eigenvalue, which is a scalar in F, yeah, which does this. So it corresponds to applying T to V corresponds to multiplying by lambda. Okay, so this is one, and two. Similarly, we can define the corresponding property for matrices as usual. So assume that A is a matrix, n by n matrix, over the field F, okay? So remember, by the way, we are restricting in such considerations to square matrices because we are talking about linear operators, right? So it's a transformation from V to itself. So it's so it corresponds to square matrices. So, okay. So, and the definition is essentially the same. So then we say that a non-zero V, a vector in the space Fn, yeah, is an eigenvector of this matrix. So it's an eigenvector of A if multiplying this vector by this matrix is the same as simply multiplying the vector by scalar lambda for some lambda in F, okay? And in this case, again, we say that lambda is an eigenvalue of A corresponding to V, okay? So in the case of matrices, we can similarly define eigenvectors and eigenvalues, where we view now these matrices simply as linear operators on this vector space Fn. Yeah, so it's like a special case of the first definition, but now we talk about matrices explicitly instead of linear transformations, linear operators. And of course, as usual, we have a correspondence again between matrices and linear transformations. So, okay, so next we recall the following theorem, which provides a criterion for diagonalizability of a linear operator. So theorem, yeah, so it allows us to determine when a linear operator is diagonalizable. So a linear operator T on V. Oh, and sorry, I haven't provided the numbers for this, I think, but you can look it up. Yeah, sorry, I don't have the numbers right now in my notes, but you can see all this material we're discussing today. I think it's from sections 5.1 and 5.2. Yeah, okay. So, all right, yeah, so theorem. So we say that the linear operator T on V is diagonalizable. Let me write diax for brevity, okay? Diagonalizable if and only if there exists an ordered basis beta for V, okay, which consists of eigenvectors for T, okay, so these two things are equivalent. On the one hand, being diagonalizable, on the other hand, admitting a basis consisting of eigenvectors. Okay, so these two are equivalent for any linear operator. This is one, and two. If we have such a basis, then we can actually write out the matrix of matrix representation of T with respect to this basis beta in a particularly simple form. So namely, we have that the matrix representing T with respect to beta, so it's diagonal and it has this particularly easy form. So we have lambda 1, lambda 2, etc., lambda n So the diagonal consists of the, well, I'll say it in a second, of the eigenvalues, and we have zeros outside of the diagonal. So where we have that lambda I is the eigenvalue of T corresponding to the ith vector in this basis beta. Okay. So it gives us this very nice presentation. So linear operator is diagonalizable if and only if we can find a basis consisting of eigenvectors for it, for the space. And then we can write out the matrix with respect to beta, where we simply have the eigenvalues on the diagonal. Yeah, that's it. So we have this nice presentation. Okay. And another theorem, which I think is theorem 5.2, tells us how to determine the eigenvalues. Okay, so we have this general theorem which gives us a correspondence. So then the next question becomes how to actually calculate the eigenvalues and how to determine the eigenvectors, right? So okay, so the first step is to determine the eigenvalues. This is the easiest part. So we have that lambda in f, a scalar, is an eigenvalue of T if and only if the determinant of T, the linear transformation, T minus lambda times the identity transformation on V is equal to 0. Okay. So this theorem gives us this recipe for determining when something is an eigenvalue. So it corresponds to finding the roots of a certain polynomial. Okay, I'll say it in a second. But first of all, we have this result. Yeah. So the eigenvalues are precisely those lambda, those scalars lambda in f, which satisfy this condition. So here, let me remind that this is the identity transformation on V. Okay. So we just scale it by lambda and then subtract from T. Okay. Corollary of this theorem. So we have the corresponding statement in terms of matrices. So for A, an n by n matrix over a field F, we have that lambda in F is an eigenvalue of A if and only if the determinant of the matrix, this time, A minus lambda times the identity matrix is equal to 0. Okay, so exactly the same statement, but now all in terms of matrices as opposed to linear transformations. Note here that, well, let me just recall. So the identity matrix as usual is a matrix which has ones on the diagonal and zeros everywhere else. And it's n by n matrix. Okay, so we have this this criteria for determining the eigenvalues, either of a linear operator or of a matrix, right? Okay, so now let's excuse me. Let's look closer at this expression. Okay, so we're interested in this expression, the determinant of such of this linear operator of the matrix. So this gives rise to a very important polynomial associated either to a matrix or to a linear transformation. So this motivates the following definition. Okay, definition. So first we define it for matrices. So for A, an n by n matrix over F, the polynomial f of t given by the determinant of A minus t in times in is called the characteristic polynomial of A. Oops. Of A. Yeah. Okay, so first of all, we all okay that this is indeed a polynomial, right? Because this expression, so the fact that it is a polynomial follows simply from the expression for the determinant. Well, it depends how you define determinant. Sometimes it's just defined as a polynomial with some additional properties, or if you just know the formula for the determinant, if you plug into it this expression, you can see that it is indeed a polynomial in terms of t. Yeah, because it just takes some sums and products, etc. there. What is the symbol after polynomial supposed to be? So which symbol do you mean? So this is just the equality. Yeah. So I'm just defining ft to be this expression.
Oh, okay. Sorry, I just couldn't tell that it was an ft. I'm sorry.
Oh, sure, no worries. Yeah, let me write it maybe more. Let's see. Let me write it clearly. I guess it's curlier than needed. Yeah. So just the equal. Yeah. So f of t is equal to this determinant. Yeah. Oh, okay. Yeah, and this is. Oh, sorry. I see. The question was actually what is this letter? Sorry, this is f. So I'm just writing f. Okay. So we have f of t is equal to that expression that follows, right? Yeah, sorry, my f's are sometimes a bit unfinished. Okay, so yeah, so okay, so this is definition of a characteristic polynomial of a matrix. All right, so now similarly, we can well, analogously, we can define a characteristic polynomial of a linear transformation. So this is part 2. So let V be a vector space of dimension, let's say n, yeah, so some finite dimension n, and we take beta to be an ordered basis for V, okay, and assume that T is a linear operator on V. So now we want to define the characteristic polynomial of a linear operator, yeah. So then we define the characteristic polynomial of T, okay, to be again f of T equal to the determinant of the matrix representing T with respect to beta, okay, minus T times the identity matrix, the n by n identity matrix. Okay, so now this, you see that this makes sense because indeed here we have a matrix, so it makes sense to talk about its determinant, right? Also, important point, we this doesn't depend on beta, yeah. So it's important that because we are only talking about, we define this as a characteristic polynomial of T instead of saying like this is the characteristic polynomial of T with respect to a given basis beta. And the reason for this is that we mentioned earlier, right? So remember we mentioned earlier that the determinant of the matrix representing T doesn't depend on the choice of beta, right? So this, we know that this part doesn't depend on beta from what we said earlier, okay? Sorry, we know that, sorry, what I'm saying, the matrix itself might depend, yeah? So again, very important difference. The matrix might depend on beta, but the determinant of this matrix doesn't depend on beta. But then this also tells us that this whole determinant also doesn't depend on beta, yeah? All right, so we have this. This notion of a characteristic polynomial of a matrix and a characteristic polynomial of a linear operator. Okay. So the next thing I need to recall is now the properties. Okay, so we have defined some polynomial. What is it good for? Well, we already saw that it's useful, for example, to determine the eigenvalues. So let's summarize some of the properties of these characteristic polynomials. Let me write it. Properties of characteristic polynomials. Okay, so let A be an n by n matrix over F. So let A be given. Okay, and we let F of t be its characteristic polynomial. Then we have the following statements about this polynomial. Okay, so the first point is that f of t is of degree n. Okay, and moreover, so remember the degree means the highest power of the variable t that appears in the polynomial. And moreover, we can write it more explicitly. Well, we can say a bit more, yeah? So in fact, f of t is a polynomial of the form -1 to the power n, tn, t to the power n, plus cn minus 1, tn minus 1, plus etc., plus c0, oops, excuse me, plus c0, right? So we have this for some scalars c0 through cn minus 1, all scalars in f. Okay, so why do we say moreover here? So the reason is that we have information, additional information about the first coefficient, the coefficient of this polynomial in front of the highest degree of the variable. Yeah, so we know that it is -1 to the power n. And the other coefficients, okay, we can't control them a priori, they're just some scalars, but the highest order coefficient is, we know explicitly. This is -1 to the power n, where n again is the dimension of our matrices. Yeah. So in particular, it tells us if it's even or odd, depending on n, right? So it's either 1 or -1. I mean, depending on whether n is even or odd. Yeah. Okay. So we have this. This is the first property. Next. So this is already, this is just a rephrasement of the theorem we said earlier. So a scalar lambda in f is an eigenvalue of a if and only if it is a root of this polynomial. So if and only if f of lambda is equal to 0. Yeah. So in other words, lambda is a root of the polynomial f of t. So determining the eigenvalues of a corresponds precisely to determining the roots of its characteristic polynomial. Okay. Then we have third point. So a has at most n distinct eigenvalues. Okay. Why? Well, because we just said that the eigenvalues are precisely the roots of the polynomial, right? And polynomial is of degree n. And we know that any polynomial of degree n has at most n roots. So that's it, yeah? So because a polynomial of degree n has at most n roots. Okay, so we are just using 1 and 1 plus 2. So the previous two statements then give us, yeah? So we have at most n distinct eigenvalues. Okay, and the last point is that if lambda is an eigenvalue of a, then we have the following. So we have that x, an element of the vector space f to the power n, yeah? So such an x is an eigenvector of a corresponding to lambda if and only if we have that x is non-zero. So remember, all eigenvectors have to be non-zero. And we have that x belongs to the null space of the linear operator LA minus lambda times the identity on Fn. Okay. So again, let's check. So this is indeed a linear operator, right? Remember LA. So given matrix A, we have LA which corresponds to multiplying by the matrix A. This is the identity transformation on Fn, and we multiply by lambda. Okay. So this again, this is nothing deep here, right? We're just expressing. This is just a way to rephrase the definition of being an eigenvector corresponding to lambda. Because X belongs to the null space means simply that, okay, let me write it actually. So because we have that LA minus lambda IFN of X is equal to 0, which is precisely what it means, right, to be in the null space. So this happens if and only if we have that LA of X is equal to lambda times X, right? Which is exactly the condition for the, well, I can say it further even. So this is the same as A times X is equal to lambda X, right? Which is precisely the condition for being an eigenvector. Yeah, so this is just a remark, nothing deep here. Okay, so we have these observations. Now we have a theorem which allows us in particular well, which establishes certain important linear independence between the eigenvectors corresponding to different eigenvalues of a given linear operator. Okay, so I'm going to switch the page, if that's okay with everyone. Okay, so let's move on. So we have theorem, and this is theorem 5.5 in the textbook. So let T be a linear operator on V, and let lambda 1 through lambda K be distinct eigenvalues of T. Okay, so let me stress here that distinct is important. So we have some distinct eigenvalues of T. Yeah, without this requirement, it's not true. What the conclusion I'm going to say is not true. So if then we have that V1 through Vk are eigenvectors of T such that the vector Vi corresponds to the eigenvalue lambda I, okay? Then the set of all these vectors, V1 through Vk, is linearly independent. So eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay, we have this. And corollary, assume that T is a linear operator on V, and the dimension of V is n. Okay, then if T has n distinct eigenvalues, then T is diagonalizable. Okay, right? So why is this a corollary? Well, because we just said that vectors corresponding to distinct eigenvalues are linearly independent, right? So then if the dimension of V is, since the dimension of V is n, and we have n distinct eigenvalues, it means we have n linearly independent vectors, which are all eigenvectors, right? So this means we have a basis consisting of eigenvectors. And by what we said earlier, this means that T is diagonalizable. Yeah. Okay. So we have this. Now, let's define a stronger property of the of the characteristic polynomial. So first, a general property of polynomials. Okay. So a polynomial f of t, a polynomial over some field f, we say that it splits over f. Okay. If there exists some scalars c a1 through an, all elements of f, there might be repetitions between them. so not necessarily distinct, such that we have that f of t can be written as the product of the corresponding linear factors. So we have c times t minus a1 times t minus a2, etc., times t minus an. Okay, so polynomial splits if it can be written as a product of some linear factors of this form. Okay, so this depends on the field f, of course. Remember, for example, every polynomial over the field of complex numbers splits, but not every polynomial over the field of reals splits. Yeah. Okay, but the very important theorem, this is theorem 5.6. It tells us that the characteristic polynomial of any diagonalizable linear operator T in LV, where V is a vector space over F, splits over F. Okay. So the characteristic polynomial of any diagonalizable linear operator splits. And I'm not saying it's if and only if. This is only an implication. Yeah. So if a linear operator is diagonalizable, then its characteristic polynomial splits. Okay. And in lieu of this, we can also make the following definition. So assume that lambda is an eigenvalue of a linear operator. Okay. With characteristic polynomial f of t. Okay. Then we define the algebraic, sometimes people stress it, sometimes not. So the algebraic multiplicity of lambda. Okay, the algebraic multiplicity of lambda. So this is defined to be the largest positive integer t. Okay, let's say, because I'm using t already. So positive integer k, okay, for which we have that the polynomial t minus lambda to the power k is a factor of the polynomial f of t. Okay, so what does it mean? This means that f of t can be written as t minus lambda times k times g of t for some polynomial g of t, right? Okay, so we take the largest k with this, so that it's still possible to write it like this. This is called the multiplicity of lambda, or the algebraic multiplicity of lambda. Okay, so this will be needed in the discussion of invariant subspaces soon. Yeah, so we recall this notion. Okay, and to conclude, so let me just define one last important thing. So the eigenspaces. So if T is a linear operator on V, lambda an eigenvalue of T, okay, then we define E lambda, and this is called the eigenspace of T corresponding to the eigenvalue lambda. Okay, so this is defined as E lambda, and this is going to consist of all vectors x and v, such that T of x is equal to lambda x. Okay, so this is all the eigenvectors corresponding to this eigenvalue. And this is the same as the null space of the linear operator T minus lambda IV. Okay, one can similarly define it for matrices. So note that this is a subspace of V. So this is always a subspace of V. Yeah. So what does it consist of? So this consisting of 0 and the eigenvectors of T corresponding to lambda. Okay, sorry, let me just finish here. So corresponding to lambda. Okay. So this is a very special, very important special subspaces associated to a given linear operator, the eigenspaces. Okay. Turns out that a lot of information, properties of the operator can be understood by understanding these subspaces, their dimensions, etc. So, and next time we'll discuss more general kinds of spaces associated to linear operator, so-called invariant spaces, or also cyclic subspaces. Okay, but this is for the next time. So today it was a reminder about all these eigen blah blah things. Yeah. Okay. Cool. So let me stop here. Yeah. Thank you as usual for coming.